this talk is going to be about the model embeddings, what is their role in the AI lifecycle, and what can we do to fully leverage their capacity. So what are embeddings? Embeddings are high-dimensional representations of samples in a dataset. They are invaluable for diagnosing real-world and complex datasets and for understanding model behavior. Getting actionable data and model insights requires much more effort than just using simple 2D visualizations, clustering, or similarity search. And I would like to highlight two of the challenges here. So the first one lies in the fact when we are trying to query the dataset for samples belonging to some concept. So the problem here is that when we're searching for a concept, the samples that belong to it might not be close in the embedding space. Even further, some of the samples might even include the concept can be represented by a weak signal, so that similarity search would also not work. The second challenge is it relates to what kind of information is stored in these embeddings, and it relates to when we are trying to debug the model and understand model failures. Now, coming back to the first challenge that I mentioned, so it arises when we're trying to query the dataset for images that belong to a certain concept. Here, there are like two main problems. So first is if we want to use the 2D visualization of embeddings, the problem here is that the dimensionality reduction that transforms the features from the high-dimensional space to the two-dimensional space is unsupervised. Now, how to actually query the dataset efficiently? Yeah? So this is where Lazlo introduces concept-based querying, which basically transform the query. So instead of just plainly looking at similarities, vector similarity in high-dimensional space, what if we can transform or learn a new feature representation that is conditioned on the query, such that the query examples are close and this representation is sparse, such that it can generalize. Now, the second challenge is, that I highlighted, is how can we group images in the dataset by the model failures, by the patterns in the model, where the model makes mistakes. So, if we just use plain embeddings, like from a foundational model, or plain embeddings from the model that we are diagnosing, we will not be able to separate images where the model makes correct predictions, whereas or where the images in a model makes incorrect predictions. So you see here, I have blue points which correspond to correct predictions, and orange points that correspond to incorrect predictions. Now, how can we do this smartly? What can we do is, if we want to understand or group images where my model is making similar mistakes, what we can do is we can backpropagate the signal about whether my model is making a correct prediction or not, and include it as part of a supervising signal when computing these embeddings, such that the embedding that we compute in the end has this is failure aware. So it has information about where my model is making mistakes and for the same reason. And here, if I look now closely at this embedding, this is this model failure aware embedding, we can see that model failures are quite distinctly separated from where the model is making correct predictions. And if we look at these clusters a bit more thoroughly, we can define clusters where my model is making, let's say, an incorrect prediction so here I have an example where my model is making incorrect prediction because it's relying to a spurious correlation that it learned, because it sees the orange color and predicts a chainsaw. But as we can see, there is no chainsaw in the image. As well as in the second example, the prediction is actually correct, but if we diagnose what the model is relying to for when it's making this prediction, we can see that it's relying at the background and not the object of interest. To sum it up, addressing specific challenges arising during the AI lifecycle requires looking beyond the standard approach when using embeddings.